All right, so this is 3.11, starting with parallel lines, postulates, and theorems. So the main idea for today is take those 4 angles that we learned about yesterday, and now we're going to basically look at only those 2 lines being parallel. Yesterday, the lines didn't have to be parallel. They could have been, or they were just 2 lines that got intersected by a transversal, and they created some angles. Well, today, our 2 lines are going to all be parallel, and we're going to make some observations. So it says here in this diagram, line AB is parallel to line CD. And I can mark it with that symbol for parallel. It's like a triangle, or you can like just make an arrow even, just to show that those are parallel. That's the symbol for it. And then as soon as we know that they're parallel, whether it's given to you in a problem, like at the top like this with the notation with the 2 straight lines, this means parallel. Or if it's given to you in the diagram with like the triangles or the arrows drawn in, that's how we know that the 2 lines are parallel. Otherwise, please don't assume that lines are parallel. Anytime you just see 2 lines, you can't just assume that they are parallel if you don't see one of these 2 things. Okay, so now it says what appears to be true, and it says if possible, use tracing paper to verify your conclusion. So I have some tracing paper here. You don't have to take any, but if you did want to try it out, I do have extras that you can always grab from like the supply area here. So what I did was I just traced onto this tracing paper the 2 lines with the transversal, and I didn't label the points or anything, but I labeled a few of the angles, 1, 2, 3, and 4. Okay. Now as I do that, I did take the whole diagram, but if I take my tracing paper and just kind of slide it down, just translate it essentially, and make it so that we kind of match up the same intersection but to this new line. So the transversal is there, but now it's at this line. If you see it, I just kind of moved it. Now it matches up exactly with what's already there. So the one I just kind of drew for 1, 2, 3, and 4, when I match it to this other one, all the angles are the exact same. So what that means is angle 1 that was up here is now angle 5. Angle 3 is the same as angle 7, 2 to 6, and 4 to 8. And yesterday we saw that those were called corresponding angles. So we're going to first just list them out. Here are all the ones that we can see that would stay the same because of like moving the tracing paper. 1 and 5 are the same. 3 and 7. And then we had 2 and 6. And 4 and 8 as well. Okay, so all that we did was, again, just looking at the beginning or the top part, and we kind of matched it and saw how every angle matched up to what was on the top. Okay, and that will always happen when you're working with parallel lines. So that's why mathematicians were seeing this pattern keep coming up, and they were able to write some postulates and theorems about what was happening every time they looked at parallel lines and these type of angles. And now we already know some other type of angles are true. Remember, we know vertical angles are also congruent. So I could list vertical angles in addition to these ones, remember, are corresponding. I'll just put abbreviate corresponding there in parentheses. But we do know vertical angles are also congruent. You can see some linear pairs in this diagram as well, between like all linear pairs there are adjacent angles. I don't have to list everything because that would take a long time. So the main idea for this first diagram is you should hopefully be able to see that these pairs of angles are all congruent to each other, just seeing how when we move the tracing paper, the angles stayed the same. And so that kind of leads us right to the first postulate at the bottom here, which says it's called the corresponding angles postulate. And remember, postulates don't have to be proven. It's like kind of like mathematicians decided that this was something that always just kind of stayed the same no matter what. And it was like you needed this one postulate to help you prove other theorems, is essentially what it was. So that's what we noticed here with the tracing paper. We only saw that the corresponding angles stayed the same, and that's kind of our thought process here, is that when we have lines that are parallel, I'm going to go ahead and draw the symbol for parallel again. It's just like the triangles, or you can draw 2 arrows. It says the corresponding angles postulate states that when 2 parallel lines are cut by a transversal, the resulting angles or corresponding angles are congruent. Okay, now instead of having so much, like it's so wordy like this, if we go to our yellow sheet, it's been kind of shortened a little bit. You can use what's here, and we're going to just learn these 4 today. So if parallel lines, then corresponding angles are congruent. And that is a postulate. Okay, you don't need to know it's a postulate, but we are going to go ahead and write that down right here as like the shorthand. So if parallel lines, then corresponding, and you can abbreviate corresponding if you want to just do CORR, that's fine too. Corresponding angles congruent. And I'm going to highlight this as we go so that it just reminds us that we can write our final like reasons, anything on a proof. This is how we could write it. It's also on your yellow sheet, of course, but that's how we're writing it down. So let's go ahead and identify those from the diagram here. Angle 1 is congruent to angle 5, just like we saw above. I'm going to draw these like congruent rings. Remember, the number of rings that you have show you which ones match together. So like 1 goes with 5, 3 can put 2 of those around it with 7. But then for 2 and 6, they also will need it. So you could put 3 rings, which is kind of getting like to be a little bit overkill, like feels like, why do we need to actually draw it this way? You don't have to, but it's just so that later if you look at this, you know which ones match together. And then this one again would have 4. Now we also know though that there's some vertical angles that would be congruent. So technically, even though I've kind of grouped them in 4 groups, like 2 pairs each, I didn't have to do that because if you know 1 and 4 are the same because they're vertical angles. So technically if 1 and 5 are congruent because they're corresponding and 1 and 4 are congruent because they're vertical, then technically 4 and 8 is also going to be congruent to 1 and 5. Those are the ones that would be congruent to each other because again, you put vertical angles together with corresponding angles. So you could just like list them all and say 1, 4, 5, and 8. That all of those will be the same exact measure, whatever the measure might be. But I can also just write my example of which of them are congruent. So I could say 1 is congruent, sorry, that symbol's not great, congruent to 5, because these are the corresponding ones. Again, 3 and 7 would be congruent, and we had 2 and 6, and finally 4 and 8. Okay, so those are the only 4 pairs of corresponding angles, and they will all be congruent because these lines were parallel. Now yesterday though, when we saw them, they weren't all congruent because the lines weren't parallel. So make sure you actually know that the lines are parallel, whether it's like given to you either in words or if it's given the symbol to you like this or with the little symbol for parallel like the 2 straight lines. That needs to be provided in order for you to see that the corresponding angles are congruent. Okay, so that's the first one. Here's the next one. Alternate interior angles theorem states that when 2 parallel lines are cut by a transversal, the resulting alternate interior angles are also congruent. So let's find them in the diagram. So from yesterday, we are finding the alternate interior. Remember, interior means on the inside of the 2 lines. So we're working with these 4 inside here, but on opposite sides. Alternate means opposite. So 3 and 6 would be the same, whereas 4 would be with 5. And again, you don't have to draw the like rings around it like that. You can also just write it down as examples, like angle 3 would be congruent to angle 6, and angle 4 would be congruent to angle 5. All right, questions on how we figured out which ones are which, and then we're going to just write out this statement that you see on your yellow sheet as well. So it says, if parallel lines then, and again you can abbreviate alternate interior. I usually will write ALT for alternate and then INT for interior. Angles are congruent. And I use the symbol for angles as well, and then the symbol for congruence. Okay, and then I'm going to just highlight this because again, this is the one that you want to use moving forward. Anytime you see parallel lines, sometimes on a proof, this may be the one that we want to use for alternate interior angles. So we'll see on a proof when we get started which one makes sense for us to kind of use, because technically we have 4 to pick from once you know 2 lines are parallel. So the next one is very similar to this. This time it's alternate exterior angles. And so it says alternate exterior angles theorem states that when 2 parallel lines are cut by a transversal, the resulting alternate exterior angles are also congruent. So here they are. Remember, exterior means outside of the two lines, and so that's the 1 and 2, 7 and 8 are the ones we're looking at, but pick the ones that are on opposite sides. So 1 with 8 and 2 with 7. So I'll write that for my examples. Angle 2 with angle 7 is congruent, and angle 1 is congruent to angle 8. Okay, and I'll move that. Okay, and here it is written out. If parallel lines, then ALT, that's alternate, EXT, exterior, angle symbol, and congruent symbol. Alternate exterior angles are also congruent. Okay, and there is that third one so far. So these three are very similar. The only thing that changes is the word for the angle, either corresponding, alternate interior, or alternate exterior. But the last one is kind of different from the rest. And so the last one talks about consecutive interior angles. So let's identify where those are on my diagram here. Remember, interior means inside the two lines. So we're working with those 4 angles, like 3, 4, 5, and 6. But then if it's consecutive, that means the same side, not alternate. So we're looking at 4 and 6 together and 3 and 5 together. So what I'm going to do is just, before I mark it with the congruent symbols and stuff, I'm just going to circle them because these ones are actually not congruent to each other. So I'm just circling them to show you the groups. Like I put 4 and 5, or 4 and 6 in one group together, and then 3 and 5. Now, if you look at it, you can kind of tell just by looking at it, though, that the angles are also not the same between 4 and 6 and 3 and 5. Because remember, 3 and 6 were the same because those were alternate interior, and 4 and 5 were the same because of alternate interior. We also knew that with like corresponding angles, 2 and 6 were the same, but then 4 and 8 were the same. And because we have some linear pairs, we know that they have to be supplementary, right? Angles 3 and 4 are supplementary, so are 5 and 6, because those are linear pairs. So we already know those are supplementary. But if 3 and 4 are supplementary, and you have alternate interior angles like 3 and 6 are the same, then technically these two pairs, 4 and 6 and 3 and 5, would also be supplementary. Okay, so that's how we're going to write this down. It says, consecutive interior angles theorem states that when two parallel lines are cut by a transversal, the resulting consecutive interior angles are supplementary. That's the only thing that's different now, is that angle 4 and 6 will be are supplementary. I'll abbreviate it. And then same with angles 3 and 5 are supplementary. So be careful when using this one, because a lot of times, like if you just want to always, when you get in the habit of always using the other ones and they're always congruent, you don't want to include this in the congruence one. This is the only one that's different from the rest. Starts the same way still. If parallel lines, then, and then you can abbreviate consecutive, either CONS or CONSEC if you want to give a little bit more of it. Consecutive interior angles are supplementary. But notice again, I did not say they're congruent. Now, if a question was like an always, sometimes, never question that said, if lines parallel, then the measure of angle 4, or I'm sorry, if lines parallel, then consecutive interior angles are congruent, it sometimes can be congruent. The scenario there would be, what if we had like vertical and horizontal lines that intersected and the angles are 90 and 90 everywhere? So then they're congruent and supplementary. So they have to stay supplementary, but you know that supplementary angles can sometimes be congruent as well. And so that's why that could be a good question for on always, sometimes, never. All right, so we know they're supplementary. That's the only one that's different. So before just kind of letting you figure it out, because I know the next page is like the practice, I do want to go through some of the practice with you so that you kind of have some understanding of like, how do I use these theorems? And then you should get some time to either start your homework or keep working through this practice that's on the back. We are going to do this proof together in just a couple minutes. It's not a very long one, but I just want to show you how one of the proofs could look like so that you can get started on the homework that has it as well. There's also one more proof on the next page, and I would say this is another great proof that I think you should do at some point, whether it's today or by Tuesday. I would do that before the quiz so you know how to do these proofs with parallel lines. Okay, but we'll do one together, and I'm going to give kind of some hints up at the top here. So let's start with the top part, and it starts with a diagram, and same thing with this diagram as the ones that were on the 3.10 practice. There's more lines. There's not just 3 lines in total, there's 4. But when you work with transversals, there can only be one transversal and 2 lines. It's, in our case, 2 parallel lines. And so specifically at number 1, it says, well, what could you conclude if A is parallel to B? Okay, so if A is parallel to B, imagine I put like the little triangle there to label it. And I can only have one transversal, right? So let's say I want to cover up this one M right here, because M is a transversal also, so is N, but I can't have 2 at one time. I can only work with one transversal and one pair of parallel lines. So now I see a bunch of angles show up. I could see which ones, it says, what can you conclude if A is parallel to B? Well, we could conclude a lot about vertical angles, corresponding angles, alternate interior angles, alternate exterior angles, all of that, right? So I could say, like, for example, 1 and 9 would be congruent because they're corresponding, but then so are 3 and 11 and 4 and 12, right? But instead of just listing all of them, could we instead write down all of the ones that are congruent to each other? So for example, what else is congruent to 1 and 9? Think about, like, if angle 1 was 30 degrees, 90 would have to be 30 degrees, but what else would be 30 degrees? Does anyone see what other angles would also be the same as 1 and 9? Yeah, what do you think, Jeffrey? Yeah, good job, because those ones are vertical angles with the 1 and the 9, so that way they are the same as well. And remember, 3 and 11 are also corresponding, so that would have to work that way too. So I could list all of them like that. Angle 1 is congruent to angle 9, is congruent to angle, whoops, I didn't write the congruent symbol, angle 3, and then 11. And it doesn't matter the order that you write them in, but I could list it all out like this, or you could write them into different pairs. Like you could say just 1 and 9, and then just 3 and 11, 2 and 10, and so on. So you could do the same thing for like the next group of them. I could do 2 and 10 with 4 and 11, or with 4 and 12, sorry. 2 is congruent to 10, is congruent to 4, and then 12. Again, in any order. But all of those are corresponding angles, but also includes the vertical angles that would also be congruent to each other. You could then also see then, if you notice, 3 and 9 were on this list earlier, on the first one. And remember, 3 and 9 are alternate interior angles. Same with here. 2 and 12 are congruent to each other here. And that makes sense because there's alternate interior angles there too. So all of the different angles we just talked about would still hold true in each of these statements. Now there's 2 more statements that you would actually write down, and it has to do with what if you cover up the N this time and just look at M as a transversal, because now you have 8 more angles to work with. So I'll write down one more and then you guys can finish up the last one. So we'll just do 5 and 13, could be one possible set of them, and then if you keep going again, you want the vertical angles, so 15 and 7. Okay, and then there's one more pair you can do for all of the corresponding ones. So that's kind of the idea on number 1. Number 2, I also want to look at that one, and then we'll move on to the proof. It says, what lines must be parallel in order for 7 to be congruent to angle 3? So like you would find 7 and 3, and notice that they're on this portion of like the group of angles, right? 7 is here, 3 is here, so I want to cover up the ones that are not being used. So I'm going to cover up that chunk there and just look at which 2 lines are parallel and which one would be the transversal. So on this one it looks like N and M are the parallel ones, with A being the transversal. So all you would write down here is M is parallel to N, or the other way around. It doesn't matter which letter you put first, but you can also write the word line M parallel to line N if you wanted to, but really we just have to identify what the 2 lines are. Now sometimes you may get both lines, sometimes it's just one of them, so you can try that out for numbers 3 and 4 as well. All right, 5 is just an algebraic problem too, where first you have to identify that angles 6 and 4 are going to be congruent because of the diagram provided where they are alternate interior angles since the lines are parallel. So if you can then set them equal to each other, it's just a solving problem at that point. So you can definitely solve to find x and then substitute back in to find the measure of what one of these is to help you then find the measure of 15. Okay, so it wants us eventually to find the measure of angle 15. This is a good one to try out later as well to practice the algebra, practice along with those angles also. Okay, and then the last one, let's go ahead and finish up with the proof. Okay, so first thing you should do is when you read through the given, mark up your diagram. So angle 1 is congruent to angle 3. We draw the little congruent rings around 1 and 3. And it says line ST is parallel to line VU. I know these don't look like lines. I could extend them. So that's kind of technically treating it as a line like this and this. And I'm going to go ahead and mark it with the little triangles to show parallel. Okay, so that's what I have so far. Notice the proof says 1 is congruent to 2, and 2 is just kind of hanging out right here on this other part. I haven't really done anything with angle 2 yet, but I'm going to have to somehow introduce it into my proof. But first, let's just start with our given, because we know that is the first step that we can do. So we have angle 1 is congruent to angle 3, and line ST is parallel to line VU. So what can kind of be tricky here is looking at the diagram, there's not just, again, 2 lines and 1 transversal. First of all, it looks like just a bunch of segments that can be confusing, but if you need to extend any of the lines, you could always do that to say, okay, they're just kind of going on forever. But what can kind of help is to redraw the diagram separately with just your 2 parallel lines. So remember, these were my 2 parallel lines. You could label them ST and VU if you want to, but here are my 2 lines that are parallel. And then figure out which transversal do I want to draw, because there's technically 2 transversals drawn in right now. One of the transversals includes angle 1. The other transversal brings in angles 2 and 3. So you want to decide which transversal do I want to include right now, and so you want to bring in the one that brings angle 2 into the proof. So that's going to be this one here. Okay, so imagine just, I'm going to extend it out, but also I'm going to draw it in here. It doesn't have to be the exact same, but just so that you can see that that's the transversal that I'm working with in this diagram. I'm just basically ignoring this other transversal that's there. Even though angle 1 is part of it, I know it's there, but I just don't need to do anything with it right now. Okay, so then I'm going to label the angles too. This one, there's a 2 right here, and then right above this transversal, there's a 3. Okay, now that you're looking at the diagram, if it helps you, you're welcome to also make it more, turn it if you need to see it more like what you might be used to seeing with the lines being parallel like this, or whichever way you need to do it. But does anyone see what type of angles 2 and 3 are from the list we just know now of our 4 angles? What do they look like? Yeah, what do you think? Perfect. Alternate interior, because they're on opposite sides of the transversal and inside the parallel lines, interior. So we know that that's going to be our reason. We're going to say if lines parallel, or if parallel lines, then alternate interior angles congruent. All right, and we want to say what those 2 alternate interior angles are that are congruent. So those are 2 and 3. Angle 2 is congruent to angle 3. And it doesn't matter which way you write them. You can say 3 is congruent to 2. But at this time, we need to figure out what my next step will be. So again, if you're ever stumped, grab your yellow sheet. We're talking about angles that are congruent. So I want to skip over everything that's talking about segments. I don't care about those. When I start to get to the angle stuff, though, it's not a right angle. It's not a straight angle. There's this mention about converting to congruence from equals. Don't want to do that because everything's in congruence here, not equals. I keep going, and the one that bisected we also can't do because nothing has mentioned that. Sometimes students want to use angle addition postulate because feels like nothing else works, but that won't show me from the diagram what 2 are equaling up a bigger one. So that still doesn't work. And then there's complementary, supplementary. Again, no mention of that. So nothing else on the front page works because all the rest was just triangle stuff. So nothing on the front page. If we go to the back, we have a bunch of stuff with equals. Remember, we can't do equals here because it's talking about congruence. So we're just left with these 3 choices here. Which one works? transitive property congruence right there. That's the one, because everything else left is all maybe talking about, although there's like right angles and congruent angles and stuff, but that's not specific to what we have here because there's no mention of those. So this is the transitive property. Anytime you find yourself needing to say that, okay, these two angles are the same, so these other two are going to be congruent, that is the transitive property. Feel free to use a highlighter to help you here. Sometimes it's helpful to like highlight the one that repeated and then highlight the other ones in a different color, or use colored pens, or whatever to help you. You can even cross off the ones that kind of repeated itself and say, I don't want those anymore. I just want angle 1 is congruent to angle 2, and I'm done because my proof looks just like that. Okay, so that's kind of where we'll stop here.